Welcome to the class of scientific computing using MATLAB. I am a second instructor of this course, and you have already seen lot of topics in numerical analysis, approximations, etc. So, now I will be teaching to you numerical methods for ordinary differential equations. At the same time, there will be a lot of concepts which will be used, which you have already done in the previous part of this course. So, just let me start with very simple differential equation, which is y dash is equal to f x y. This is first order differential equations, and most of the real life applications cannot be handled by analytical methods. That is what we all know. That is why numerical methods play an important role. So, first of all, we should understand why differential equations are useful. In fact, I do not need to explain you much about it, because we already know the application of differential equations. There are many physical quantities in real world application which we want to trace. So, with the help of this differential equation also, we are looking the behavior of y with respect to x. If you look at as a real world problem, y is some physical quantity and x is some another physical quantity. If you look at as a mathematical point of view, y and x are, y is a dependent variable and x is a independent variable. So, in real world applications, whenever we want to see the behavior of many physical quantities with respect to some another quantity which is x here. So, in that case we model real life applications with the set of a differential equations. Of course, all of us know to solve differential equations we need initial conditions or some set of a conditions. If this is a first order differential equations and only one condition is prescribed at one point, which is a initial point. If it would have been a second order differential equations, we need two conditions to solve that. And if those two conditions are prescribed at the one point, that is called initial value problem, and if those two conditions are prescribed at two different points, they are called boundary value problems. So, I have made a clear distinction between initial value problem and boundary value problem for a second order differential equations. But here just for simplicity we are considering only a first order differential equations together with initial condition. That is why all together this is called initial value problem, initial value problem, and in a short form it is called IVP. Okay. We have seen different variant of a differential equations as well. If f is 0, we call it as a homogeneous differential equation. If f is non-zero, then we call it as a non-homogeneous differential equations, and depending on f x y, we can also call it as a linear or non-linear differential equation. That is altogether different ball game. But right now our aim is to solve this initial value problem by numerical method. But before going to the domain of a numerical method, we should first of all we should make sure whether we can solve this initial value problem analytically or not. We should solve means whether there exists a solution as well as this solution is unique. So, all of you must have seen existence and uniqueness theorem for initial value problem. So, under that theorem we put some conditions on f, and under those conditions of f we guarantee that solution will exist as well as will be unique. So, before going to the domain of a numerical solution, we should make sure that solution exists as well as solution is unique. After that we try to solve it numerically. Because if there does not exist a solution and we are trying to solve it numerically, it is a wastage of time. At the same time, if there are infinitely many solutions and we are trying to solve it, so sometime we will get one solution, other time we will get another solution, and we will be not sure which is the solution. So, numerical solution play an important role once you are sure that this problem has a solution. So, because there are many theorems in the numerical analysis as well as in functional analysis, with the help of those theorems we can predict solution exists, and we do not know the exact form of a solution, but at least we can predict whether solution exists and the solution is unique also. Okay. So, now we are considering the following initial value problem. So, what we do initially, we discretize, because initial point is given to us, x0 is the initial point. From x0 we have to find the solution at x1, which is at x0 plus h, and then we have to find a solution at x2, which is again x0 plus 2h, and xn is x0 plus nh. Again, just for simplicity, we are considering that the grid is equally spaced, means x1 minus x0 is h, x2 minus x1 is also h, and xn minus 1 is also h, means the difference between each grid point is same. We can also work for a non equally spaced grid, but that is we will see later on. Right now, for simplicity, we are considering equally spaced grid. Okay. So, now to solve this differential equations numerically, what is the first step we should take? This is y dash is a derivative. So, we have to approximate this derivative first. Okay. We have to approximate this derivative first. You must have seen lot of methods to approximate derivative earlier in this course, like forward Euler, backward Euler, central difference to approximate the derivative, etc. So, we will be recalling those concepts in due course of time, but before that let me start with Taylor series method, which is one could see as a oldest method to solve a initial value problem. So, in Taylor series method, what we do, we express yx with the help of Taylor series. Okay. We write Taylor series of a function yx around y x naught. We write the Taylor series around yx around point x naught. So, if that is the fundamental idea behind the Taylor series, if we retain only first initial terms, then it will be called pth order accurate. In not initial term, if we retain only first p plus 1 term, then it is called pth order accurate method, and truncation error will be this. Okay. Then it will be called pth order accurate methods, where zeta lying between x and x naught. I am not going into the detail of explaining you Taylor series, because all of you know Taylor series already. So, let me start with forward Euler method, which is a special case of a Taylor series method. How it is a special case of a Taylor series method? So, in forward Euler method, what we are doing basically, if we want to evaluate yx at x is equal to xn plus 1, then we are writing the Taylor series around point xn, and this Taylor series will be this. Okay. So, basically just if you have seen the previous version of a Taylor series, we have substituted x is equal to xn plus 1 here. So, in forward Euler method, we are retaining only initial two terms, means we want to retain only these two terms. If we retain only first two terms, then method is called first order accurate. Why this method is called first order accurate, that I will explain you in a while. and this is called Euler methods. Then the scheme will be, you know, there is a lot of difference between going from here to here, because from here to here what is the difference you observe? We have dropped this error term, we have dropped this error term. So, yxn plus 1 is a exact solution of a differential equations at point x is equal to xn plus 1, while yn plus 1 is a solution of a this difference equation. There is a difference between differential equation and difference equation, because we obtain the difference equation after neglecting this error term. So, the solution of difference equation approximate the solution of a differential equation. That is the whole idea. So, yn plus 1 is a solution of a difference equation, while yxn plus 1 is a solution of a differential equations. So, that is what I wanted to say you. The above equation is called the difference equation. It approximates the differential equation in the sense that solution of difference equation is the approximate solution of a differential equations. So, here we have kept only initial two terms, this and this, and we have neglected this term. After neglecting this term, we come to this step which is a difference equations. Okay. So, that is the whole point behind forward Euler methods. So, what is the local truncation error? Local truncation error will be this, where xi n lies between xn to xn plus 1, and global truncation error because we have started from x naught and we wanted to compute till xn's. So, we have accumulated this local truncation error n times, that is why we are multiplying this global truncation error with the number n. So, nh is again a constant which you can observe from here. So, that is why global truncation error is order of h. So, basically always the order of global truncation error will be 1 less than the order of local truncation error, and method is always known with the order of a global truncation error, not with the local truncation error. That is why it is called first order accurate method. That is what I said, that I will explain you later how you define it is a first order accurate method, because we define the order of the method as the order of a global truncation error. So, this is called forward Euler method. Why it is called forward Euler method? Because Euler is the name of a scientist who invented this method. Why forward world is coming? Because we are going one step in the forward direction. We have started our things from x naught and we are computing at x1, and then once we know the solution at x1, then we will go to the x2. So, we are moving in the forward direction, that is why it is called forward Euler method. I have also explained you how you will define the local truncation error, how you will define the global truncation error. So, now let me give you the formal definition of this. A numerical method is said to converge to a solution of yx of a given initial value problem at some point if global error, which is this. So, how you define the global error? The solution of a differential equation which is y at xn minus solution of a difference equation. That is how we define the global error. So, basically global error, the maximum of global error should tends to 0 as h tends to 0. It converges at a pth order rate if we say En is order of this. Okay. So, basically at x satisfy mod of En tends to 0 as s tends to 0 and n tends to infinity. Okay. It converges at a pth order rate if En is order of Hp for some p is greater than 0. So, this is a more formal definition how you define the convergence of a numerical method. So, again we look at this definition, and using this definition we will prove when Euler method is applied to following initial value problem, it converges, and the order of convergence is first order because it converges with the first order. That is what you can see here. So, basically the theorem says Euler methods applied to the following initial value problem, and where lambda is some complex number and g is a continuously differentiable function, that is the conditions we are putting, converges, and global error at any x from 0 to xn will be order of h. So, basically that we have seen earlier also that here Euler method means forward Euler method, converges, the order of method is first order, that is why global error will be order of h. So, here we will see more formally. Here we have also taken just for simplicity we have taken the specific value of fxy, which is lambda y plus gx. Okay. So, the proof goes in the following manner. We define En plus 1, let me change the color so that it is more visible to you. Yes. So, in the proof we define En plus 1 is En plus 1 is equal to y at xn plus 1 minus y n plus 1. So, this is a solution of a differential equation again at x is equal to xn plus 1, and this is the solution of a difference equation. That is how we define the error, which we have seen here also. So, here also you have seen how you define the error. So, here basically truncation error plays a role. Truncation error decides the order of the method, that we have already seen. So, here you see I am expanding this yx as a Taylor series function around point xn, and I also write what is the difference equations I have written. So, yxn plus 1 is equal to y at xn plus h y dash at xn plus truncation error, which is Tn plus 1 is basically a truncation error. I am denoting truncation error minus yn minus h lambda yn. So, then we do some specific calculation. Y at xn minus yn can be so this and this term jointly can be written as a En, and then I substitute the value of y dash at xn, which is will be lambda h y at xn plus truncation error, and then I clubbed this term with this. So, again by rearranging the terms I get En, and then lambda h, lambda I can take it common from here, and then yxn minus yn will be En plus Tn plus 1. So, again 1 plus lambda h En plus Tn plus 1. Tn plus 1 is a truncation error as we have already seen. So, substituting this is a iterative procedure, because as I told you we will start from x naught. So, x naught corresponds to n is equal to 0, and then we will compute x1. So, E1 is basically a T1, and E naught is, because in initial conditions we are not making any approximation, therefore, E naught is 0. E2 is this 1 plus lambda h T2. So, here we substitute the value of E1 from the previous step and we get the following. So, in a similar way we write E3 1 plus lambda h E2 plus T3, and then we substitute the value of E2 from the previous steps and we get the following terms. So, basically if we start doing this in a recursive manner, we get En in this way, which can also be written this way. Okay. So, till this point I hope it should be clear to everyone. Now, we are using some inequalities. One of the inequalities I will be using 1 plus lambda h n minus j, which is this term is from here. So, we want to bound that term. So, that is basically that we all know, and we are writing in the following fashion. So, this is can be written this way, because x n minus j is basically h into n minus j, that we all know, and which can be written mod, because x n minus j will be always less than x n. So, with this inequality we can write this nh is x n, this we have also seen here. So, you and Tj is our we also want to bound this term Tj, which is Tj is less than Ch square, okay, because Tj is the truncation error involving in one step, that is what you could see. T1, T2, T3, T4, these are the, we are bringing truncation error in each step. So, that is Ch square for some constant C. So, when we substitute this here, we substitute the bounds for Tj as well as bounds of this inequality here, okay, and this term is Ch square, we can take it common, Ch square, okay, and this is again independent of j. So, that is why n and this term has come. So, Ch again we can write Ch, and nh xn is basically nh. So, using the value of this variable we can formally write this as a C1h. So, this is a more formal way of proving the convergence, because we are saying, so as s tends to 0, En tends to, absolute value of En tends to 0. So, since En is order of h, hence Euler method converges with the first order rate. Okay. So, in this theorem, just for simplicity we have chosen a specific value of fxy. You can also work for general fxy, but in that case you have to use some inequalities, because here we are also making one condition that g is a continuously differentiable function, but you can do for general fxy also in the similar way. Okay. So, finally, we have proved that forward Euler method converges, that is one thing, and converges with which order. Okay. The rate of a convergence is first order, the rate of a convergence is first order, or the order of the convergence is first order. So, now in the similar way you can ask me that I can retain more terms in Taylor series method if I wanted to achieve high order method. Yes. So, the answer is yes, I can work out with the second order method, third order method, fourth order method, similar way. But what will be the disadvantage you feel if I will be keep adding this way? Because if I am retaining 2 terms, I have to calculate the approximation of y dash. If I retain 3 terms, I have to calculate the approximation of y double dash. So, similar way, which is a very complicated step, because for some initial value problem even analytically you cannot compute the derivative very easily. Okay. So, that is why Taylor series method is acceptable to the community who do numerical methods only up to first or second order. It is not acceptable beyond that, because the computation of approximation of high order derivative is a tedious task. Okay. So, some people also if we retain 2 terms, this is called TS1 method. if we retain p plus 1 term, this is called pth order methods, because here we are retaining 2 terms and it is called first order method, and if we are retaining first p plus 1 terms, then it is called pth order method. That is what we have seen here also. If we retain p plus 1 terms, then it is called pth order methods. But as I told you, it is not very practical to retain more and more terms. I have also told you the reason. That is why, so now the question is, it is a first order accurate method, how we can achieve high order methods. Okay. So, for that reason I am going to explain you a trapezoidal method. What this method says? This method says, if we retain only first 3 terms, the method is second order accurate and called modified Euler method. Then Taylor series will be this. So, basically I am saying, if you retain first 3 terms, it will be called Taylor series method. First 3 terms of Taylor series. So, if we are retaining first 3 terms of a Taylor series, we get second order accuracy, but at the same time at each step we need to calculate the y dash, which is again a very costly step. That is what I have already explained you. So, to overcome this problem, what we do? We write y dash in terms of y dash by Taylor series. So, we are doing some manipulation in the Taylor series. This is the Taylor series of y dash around point xn. This is the error term truncation. So, if by rearranging the terms we get the following. So, you must have already seen in these things in the when you must be doing a numerical approximation of the derivatives. Okay. So, now we are writing y dash xn in terms of y dash. So, if I neglect this term, this will be approximation. Okay. So, now I am substituting the value of y dash here in the Taylor series, means I am substituting this value of y double dash here, and after neglecting error term, which is order of h cube from here, and again this is order of h cube, because h square is multiplied with h and this will be order of h cube. So, after neglecting this term we get the following equations. So, again what is this? This is a difference equation. This is a difference equation. So, in numerical method basically we are not solving the differential equations. In numerical methods we are solving the difference equation, which the solution of difference equation approximate the solution of differential equations. That is what we have seen earlier also. So, the local truncation error of this method will be order of h cube, that is what we have already seen, and global truncation error will be same way which I have explained you earlier, it will be multiplied with n. You can also prove it in a more formal way, the way I have done for a forward Euler method, but this is more easier. So, that is why, because I do not need to prove the theorem in each and every case. So, this is order of h square. So, trapezoidal method is a second order accurate, because the order of the method is governed by the order of the global truncation error. That is what we have already said. So, the above method is called trapezoidal method and it is second order accurate. Trapezoidal method is a implicit method. Okay. So, here there is a point to explain. What do you mean by implicit method or what do you mean by explicit method? So, this implicit and explicit you must have seen when you are, what is the meaning of a explicit function and what is the meaning of a implicit function. So, if you keep those distinction in your mind, I can explain you what is the meaning of explicit and implicit method. In the case of a forward Euler, the difference equation which we have used is yn plus 1 is equal to yn plus h yn dash. Okay. So, in the left hand side there was a term yn plus 1, while in the right hand side there was no term involving yn plus 1. Okay. So, that is also the meaning of explicit function when we write y explicitly as a function of x, while implicit functions are defined in the following way. When you cannot explicitly write y in terms of x. So, the same thing goes here, yn plus 1 you can write explicitly in the form of a yn, while in the case of a trapezoidal method in which I use the following difference equation, yn plus 1 term is also involved in the right hand side. That is why this method is called implicit method. Okay. Contrary to the forward Euler method, which is a explicit method. So, now you can think of doing some examples, or you can think of doing some situations where explicit method is more beneficial or implicit method is more beneficial, or means what is the advantage and disadvantage of explicit and implicit method. We have so far we have seen Taylor series methods, which the order of the Taylor series method is defined by how much term you keep in the Taylor series. So, the forward Euler is a special case of a Taylor series method and it is also called TS1. Forward Euler method we have derived by retaining just initial 2 terms of the Taylor series, but the trapezoidal method we have not derived just by retaining the initial 3 terms. Okay, we have done some extra because we want to avoid the approximation of second derivative. That is why we have done some extra calculation, and that is why this is not TS2 method. Trapezoidal is not a TS2 method. We have done something extra, and that is why it is with the different name, which is a trapezoidal method. So, now the next question which can come to your mind, that why I have used only why here I have kept 2 terms, because I also want that the error which I am neglecting in this part, means specifically in this part, that should also be order of h cube, because if this is order of, if after multiplying, if it would have been order of h square, and after multiplying with h square it would have been order of h4, and here it is order of h cube, or means this error can be order of h4 and this is order of h cube, or if it would have been order of h and this would have been order of order of h square and h cube. We want to retain the same order, okay, not this, not this. I will explain you later why not, okay. But right now I wanted to retain the same order, that is why we have here we have retained only 2 terms of the Taylor series, and after that I will neglect this as an error. Yeah. So, basically we have seen Taylor series methods, forward Euler method and trapezoidal method. So, all Taylor series methods you can see they will be explicit methods, though in detail we have seen only one special case of a Taylor series method, which is a forward Euler method. But if you retain 2 terms, 3 terms, 4 terms without doing any manipulation, then also it will be explicit method, okay. So, now let me go to the next slide, which is a advantage and disadvantage of the numerical method. So, here we will take few examples. By those examples you will understand what is the advantage and disadvantage of explicit and implicit methods. So, in Now we are considering the following example, this, okay, which is a second order differential equations together with two conditions. Both the conditions are prescribed at 1.0 and that is why it is called initial value problem. The abbreviation which we have used for initial value problem is IVP. We will convert this second order equation to a system, that we all know how we can convert high order differential equation into a system of differential equations, first order differential equations. So, I substitute this u is equal to y, v is equal to y dash, then this solves the system, this is just a typo, this should be the, okay. So, v dash is x minus ux and u dash is vx, and I get these two conditions, u is equal to u0 is equal to alpha and v0 is equal to beta. Sorry, this should be y dash, okay. Okay. So, if we solve above system by forward Euler methods, okay. So, what will be the difference equation of a forward Euler method? We have seen un plus 1 is equal to un plus h into un dash, which is basically v here, vn, and we will also write a difference equation for Vn plus 1 here. So, Vn plus 1 is equal to Vn plus h. So, basically Vn dash is this, okay, xn minus un, which we substitute from here, with u0 is alpha and v0 is beta. Using the initial value of u and b in the above system can be easily solved, which we all can understand. Hence, now if we solve the system by trapezoidal method. So, this is the idea I have given you, how you can solve a system of differential equations using forward Euler method. And now let me come to the trapezoidal method. So, in trapezoidal method, un plus 1 is equal to un plus un dash plus un plus 1 dash, that is the difference equation. We have substituted the value and we get this thing. Similar things we can do for Vn plus 1. So, here to find the value of un plus 1, we need the value of Vn plus 1, that is what you can see from here. Hence, we have to solve the algebraic system, which is again a very costly step, as there could be n number of equations with large value of n. Hence, it is better to use forward Euler method to solve a system of OD. If for a system of OD n is very large, or you can say the, here we have started, why we have ended with a 2 by 2 algebraic system, because we started with second order differential equations. If there are, the order is more, the order of this system will also be more, that you must have seen in some theoretical course of differential equations, okay. So, and solving a algebraic system of high order is a costly step, that all of us know, and you must have also observed in the earlier part of this course, that Ax, solving Ax is equal to b is a costly step once the order of A is large. 2 by 2 system is anyway you can solve it by hand also, but we are developing numerical methods not for 2 by 2 case. This is just for simplicity we are taking this problem, but our motivation is for a general and complicated case. Okay, so, if you look at this example and you solve it by forward Euler and you solve it by trapezoidal method. So, the first difference which I can observe between forward Euler and trapezoidal method is, forward Euler is a first order accurate method, while trapezoidal method is a second order accurate. So, of course, using trapezoidal I am getting more accuracy, okay, that is one thing, but at the same time I am involving one extra step which is costly. So, means computation is more. So, if you ask me in terms of computational efficiency, forward Euler is more simpler. The computational efficiency is more because you are not solving an algebraic system. But in case of a trapezoidal method, to solve a system of differential equation, you have to solve a algebraic system. So, that is the one difference you could observe between explicit and implicit methods in general. So, you can say forward Euler is a special one category of a explicit method. Similar thing, trapezoidal method is also a category of a implicit methods. Now, let me consider another example where we are considering the following initial value problem, okay, and with the following initial conditions. Okay. So, this time this is a first order. If we use forward Euler method to solve the difference equation will be this, and so in y0 is given to me, and then I can compute y1, then from y1 I can compute y2. So, we can solve the difference equation and we get the first order accuracy. And similar things, if we approximate it with the trapezoidal method, we use the following difference equations, okay. And so, for a linear problem we are not taking any extra step. So, for a linear problem as well as this is just a first order. So, again using the initial values we can solve the above difference equation to find the approximate solution of a differential equation, and the method will be second order accurate. Due to high accuracy, trapezoidal method will give the better approximation than the forward Euler. That is what we have expected, okay, in case of a linear EVP. Hence, so far we cannot say whether the implicit or explicit method will give the better approximations, because in one case of course I am saying trapezoidal method will give the better approximation because it is a high order method. But if I compare implicit and explicit method of same order, then which one will give you a better approximation? That you cannot say, because both are under same order accurate methods. In that case, depending on the problem you have to choose, or depending on the means how much computational efficiency you want from the problem. Okay. So, that later on I will take one example of a nonlinear problem also, and I will explain you how it works. So, now let me start with Adam-Bashforth method. What is Adam-Bashforth, or again Adams is also name of a scientist, Adam-Bashforth. So, they are basically under this category we learn how to develop a high order explicit methods, because so far we have seen forward Euler method which was a first order, but how to develop high order methods but explicits, because trapezoidal method was implicit. Okay. So, again of course, if we retain all these terms as such, this will be called Taylor series method of second order. If we do some modifications here, that is what we have seen in Taylor's trapezoidal method. We develop trapezoidal method. If we retain first three with some another modifications like this, y dash xn, I am writing y dash xn in the following way. Okay. So, this again you getting this step is not very tedious. The same way like you have done earlier, you can write a difference equations and you can get it like you have done here. Okay. So, then the scheme will be, so if I am retaining this order of h square. So, again why I am retaining order of h square, that should be clear to you. I want the approximation of this term, whole term, the error which I neglect from this term and the error which the order should remain same. It should not be different. Why it should not be different? That is what I will explain you later. So, with this yn plus 1 is equal to yn plus hy dash xn, and here I substitute the value of this here, after that I will get this thing. Okay. So, it is a two step. So, again you will call it as a explicit method or implicit method. In my opinion, it is again a explicit method, because the left hand side contains yn plus 1, while right hand side does not contain any terms which involves y at n plus 1. So, it is again a explicit method, but here what is the cost I am paying to achieve high order explicit method? That it is a two step explicit schemes of order 2. What is the meaning of two step? Like if I am going from y0 to y1 in a one, this is called single step method, one step method. But here to compute at the value of y2, I need the value of y0 as well as I need the value of y1, okay, because if I substitute n is equal to 1 here, so this will be y2 y1 plus h by 2 3 y1 dash minus y0 dash, okay. So, basically to compute the value at the following grid, so this is at x0 corresponds to x1 corresponds to x2. So, to compute y2 I need from this, I need from this. So, that is why it is called two step method, while forward Euler method was a one step method. I need previous values only one step previous. In this case I need two step previous values, okay. So, that is why it is a two step explicit schemes of order 2. So, now this is a Adam-Bashforth method, which is a general method to derive high order accurate explicit methods category. Similarly, how to derive high order accurate methods, but implicit. This time I am saying implicit, which will be come under the category of a Adams-Moulton method. Okay. So, if we, so here again we will be playing with the Taylor series. So, here I am writing the Taylor series in the following way. Okay. If you want to evaluate yx at xn plus 1, so basically xn is xn plus 1 minus h, that is what we are doing. So, here also means Taylor series is written in the following way. If we retain only first two terms, again, so if I am retaining first two terms, this term will be neglected, not this term exactly, the remaining terms will be neglected. So, the local truncation error will be order of h square and global truncation error will be order of h. That is why here itself I am writing this method is called first order accurate and called backward Euler methods, because the order of a local truncation error will be 2, and that is why again with the same calculations which we were doing in case of a trapezoidal as well as in case of a forward Euler, the global truncation, the order of global truncation error will be order of H. That is why it is called first order accurate method, backward Euler. But why this time backward? That is what I will explain. So, if so here the difference equation in case of a backward Euler will become, this is yn plus 1 minus h, okay, yn dash. So, basically it means yn plus 1 is equal to yn plus h, okay. So, why it is an implicit method? Because the term which is involved in the left hand side is also involved in the right hand side, okay. That is why this is called implicit backward Euler method, okay. Clear to everyone? So, in a similar way with some modifications, again I can say how to develop high order implicit methods, okay. How to develop high order implicit methods, and those methods will come under the category of a Adams-Moulton methods. Like in the previous case we have seen how to develop high order accurate explicit methods. They come under the category of a Adam-Bashforth methods. So, basically the whole idea is Adam-Bashforth methods can be of different order as well as Adams-Moulton method can also be of different order, depending what type of calculations you, what is the desired order you do. So, now if now I will I wanted to retain 3 terms, okay, that is the only idea with some modifications. So, I am writing y dash in the following way. I will use the following approximation for the derivative. After substituting this value here, I get this, which is basically the same difference equation which we have seen in case of a trapezoidal method. Okay. So, and so here let me stop in this lecture here itself. In the next lecture geometrically also I will explain you why this is called trapezoidal method. So, in a nutshell, in today's lecture we have seen Taylor series methods, Adam-Bashforth methods, Adams-Moulton's methods. But we have seen only few first order as well as second order Adam-Bashforth formulas. Some people also call it as a formulas, as well as in Adam-Moulton's case also we have seen first order method, we have seen second order method. First order is backward Euler, second order is trapezoidal. In case of a Adam-Bashforth methods, first order is forward Euler and second order is not, I am not specifying it with some special name, and the difference equation of a second order method is this, which you can observe from here. So, here also the only, if I compare trapezoidal method with the second order Adam-Bashforth formulae, the only difference, this is a 2 step, this is a 1 step. So, later on I will also explain you what is the advantage and disadvantage of 1 step, 2 step methods. Like at least so far I have shown you one disadvantage of implicit method over explicit methods in case of a system of differential equations. If you are solving just one first order linear differential equations together with initial value, then it is not a disadvantage. But in case of a system of differential equation which you get when you solve second order differential equations together with initial conditions, in that case it is a disadvantage. So with these things I am closing now. Thank you very much for your attention.